In several of the topics we've looked at in this unit of class, we've used a data set that we built based upon our color shape pieces set from our kit. We picked 3 features to use: color, number of sides, and size. But we entered values for each of these things by hand. If we want to use our AI knowledge to improve our machine vision capabilities, we'll need to obtain values for these features automatically, just by processing the image. This process of obtaining feature values from some raw data, like an image, is called feature extraction, and it's an indispensable part of the whole AI for machine vision process. Let me show you what I mean. Here's how the whole AI for machine vision process goes. First, we present our algorithm with images of the training data objects. If we're using a supervised learning process, we might first show all of the objects in class 0 together, then show all the objects in class 1 together. If we're using an unsupervised learning process, we might show all of the objects in both of the classes together. Next, our algorithm will process the images to separate out the objects. We already learned how to do this part using masking and a connected pixel algorithm. Then we do feature extraction. We find values for each feature of each object. At the end of this step, we have a training data set like we used in each of our machine learning topics. Next, we use whatever machine learning algorithm we've chosen to learn the training data. Now, we present our algorithm with an image of a testing data object. Using the model obtained from the last step, the algorithm tells us which class it thinks the testing data object belongs in. So, if you choose to do the object sorter final challenge, this is what you will do. Today, we're going to fill in the one missing step that you haven't learned yet: feature extraction. To get started with feature extraction, we need to start by figuring out what features we want to extract. There are a couple of important characteristics a feature needs to have in order to be a good choice as a feature to be extracted. First, it has to be possible to get the feature automatically from the data that we have. It's even better if it's easy to get the feature automatically from the data that we have. For example, suppose we're trying to write code to get our algorithm to learn to tell the difference between dogs and cats. We might decide that the sound the animal makes would be a great feature to use. We might say that number 1 represents meow and number 2 represents woof. But if the only raw data that the algorithm has is images, then this isn't a good feature to use. Now, of course, this is an obvious example, and sometimes it's less obvious what is a possible or easy feature to get. For example, with our color shape pieces, we've used number of sides in our handmade database, and we've also used size. Size would be a really easy feature to get from a picture. We could just sum up all of the pixels that belong to that one object. But number of sides might be more difficult. We'd need to do some kind of edge extraction, separate the edges from each other, figure out which edges are straight, and then add up the number of straight edges. We might decide that this feature is too difficult to get. Next, it has to be that the feature is useful for telling the difference between the classes of data. Sometimes this is obvious. The cat and dog sound example is pretty straightforward. Using meow versus woof is a good feature according to this requirement because it's pretty rare to find a cat that says woof or a dog that says meow. If we would plot the sound made by cats and dogs on a line like this, we would find that there is very little or no overlap in this dimension. In other words, the data is completely separable using this feature. We want to try to pick features that will result in the data being as separable as possible because our machine learning algorithms will do better with data that is separable. Now, there is a third requirement for picking features that is a little harder to understand. This requirement is that we want to pick as few features as we can while still being able to distinguish between the classes of data. This is because of something called the curse of dimensionality. The curse of dimensionality tells us that as the dimensionality of our data increases, that is, as we add more features, the amount of training data that we need to cover the space increases exponentially. Let me show you an example. Suppose we decided to only use one feature, meow versus woof, to tell the difference between cats and dogs. In this case, we only need 2 data points to cover the range of possible values for this one feature. Now, suppose we also decided to use the loudness of the sound as a second feature. Now, the data is in 2 dimensions. One dimension is what the sound says, and the second dimension is the loudness. Now, we have 4 values, 2 squared, needed to cover the space. Loud woof, quiet woof, loud meow, and quiet meow. Now, suppose we added a third feature, how long the sound lasts. We now plot our data in 3 dimensions, and now there are 8 values, 2 to the 3rd power, required to cover the space. Loud long woof, loud short woof, quiet long woof, quiet short woof, loud long meow, and so on. So we should always only add another feature to the data set if it is needed to help the separability of the data. Let's take a closer look at how this works by actually extracting some features from our color shape pieces. Start out with the code that we ended with in the object labeling lab. Do a save as on this code so you can get back to it later in case something goes wrong. Now, the first thing we'll change is to make this work not only with red only, but also with blue only and green only. So here's the code you should be starting with, the code from the masking and image segmentation lab. We already have the code for extracting the red, green, and blue images, but we also want to get the green only and blue only images. So I'll copy this line, paste it a couple of times, now the green only image should take green, and we should subtract blue and also red. And then blue only should take blue and subtract green and red. These next lines are the thresholding lines. Lines where we take the grayscale image that is red only and convert it into a binary image that has only 0 black pixels or 255 white pixels. We've thresholded this image around the value 50 so that any pixel that's brighter than 50 becomes white and any pixel that's darker than 50 becomes 0. You might have a different threshold value here, and that's okay. We'll have to play around with this threshold value to get values that work for us. But we need to do this for the green and blue only images as well. So I'll copy these 2 lines and paste them twice. And instead of red only, we're going to do green only. And here we'll do blue only. Okay, and we're also going to copy this. Now, I'm going to make a couple of changes to this that will probably improve the results. Here you have green only as being green minus red minus blue. Let's take out the minus blue. And here where we have blue being blue minus green minus red, I'm going to take out minus green. Because green and blue colors look so similar, you can often get better results here. Also, I've found that I need my green to be a little bit more sensitive, so I'm going to turn this to 20, and your actual thresholds might be a little bit different, but once we have this set up, we'll test it, and I'll show you how to get those numbers a little bit better. Now, after we have the red, green, and blue only, I actually want to get one image that has all the objects regardless of what color they are. And I'm going to call that new image all only. All only is going to be equal to red only plus green only plus blue only. Then when we do this opening operation to get rid of the image noise, instead of doing this on the image red only, I want to do this on all only. Okay, now let's scroll down a little bit. Here we have some lines to show the different objects. I want to loop through this. Since I don't know how many objects we're actually going to have, I can't just give a bunch of lines to do the first, second, third, and fourth object and so on. So here's how we can do that. Up here, I'll create a variable called I and set it equal to 1, and then I'll do while I is less than np.amax labels, so that this loop will run up to the largest value in our labels matrix. But I also don't want it to get out of hand and just give me a lot of images. So I'll say and I is less than 10. So I won't ever let it give me more than 10 objects. Now, inside this loop, let's take this first group of object matrices, and I'll just call this object, obj, is equal to B, that's our object matrix, equals equals, instead of 0, let's do I, so that every time through this loop, we'll pick out the next object. Now, object is equal to object converted to an 8-bit integer. Then object, anywhere object is greater than 0, should be equal to 255. And then we will im show, and we don't know which object it is here, so we'll be looping through it, object space, and then we'll do a string concatenation plus, we'll convert the number I into a string. And then the thing we want to print is object. So the next line here is I equals I plus 1. And then we can delete the rest of these groups here. And finally, here we want to show all only instead of red only. Now, let's go back up to the top of the screen and prepare to create our plots. There are a few more things we need to import up here in order to be able to make our 3D scatter plots. So import matplotlib.pyplot as PLT, and then from mpltoolkits.mplot3d import axes 3D. Then we'll create a new figure and we'll set up the axes of this figure. Then down at the bottom, here we want to find the RGB values of each object. These are the first features that we'll try. Right now, we're not sure which features will be good according to our 3 rules. So we'll just try some features and then we'll look at the data and see what we have. So we'll create some new variables, average red, average blue, and average green, which will keep track of the RGB values of each of the objects we place in view. So we're going to start with I equals 1, and while I is less than Amax labels, I think this is supposed to be np.amax. I'll go back and change that in a bit. We'll set up the object matrix, and then the red values of all of the pixels in this object matrix will be equal to the object matrix times the array red. Since the object matrix has a positive value only in those pixels which belong to this object, by multiplying the object matrix by the red, blue, and green matrices respectively, we can get matrices which store the red, blue, or green value in each of the pixels only that belong to the object, and all the rest of the pixels will still be dark. Now, we'll also keep track of the size of the object, and we can get the size of the object by summing together all of the pixels in the object matrix. We can use size as another feature, but we also need to know size in order to get the mean red, blue, and green values. So the average red value will be equal to, here we'll append the new value onto the old value. We'll add up the red values and then divide it by size, and that will give us the average red value of this whole single object. So we'll do the same thing for the blue value. We sum up all of the pixels of the object, just their blue values, divided by size, and then we'll do the same thing for green. The reason we're appending here is because we want to have it in the end a whole list of the average red, green, and blue values for each object that's in view of the camera. So we'll increment I here. Then outside of the loop, we'll create a scatter plot. I'm doing this outside of the loop because we don't want to create the scatter plot until we've calculated the red, blue, and green values for every object that's in view. We'll plot all of the points in the blue color. I'll also create some labels so that we remember what each feature means. So the x-axis is the red value. The y-axis is the blue value. And the z-axis is the green value. And we need to show the plot. Now we'll try and run this. Oh, and we get an error. I forgot to put the colon on my while loop. Let's try this again. Okay, here's the image that I get. You see how my background looks a bit pinkish instead of being white? I'm just going to stick my hand in the view close to the camera, and that will force it to do a little bit of a white balance that will fix that pink background. So here is the image before it's been masked. Then here's the after masking image. Everything looks good. There isn't much noise, and I see all of the objects here. So far we're good. Now we want to see our actual data points. But we made an error here. I need to do np.amax labels. Let's try this once again. Okay. If you get a runtime error, don't worry about it. Just click OK. It'll probably run anyways. I have a pink background, so I stick my hand in the screen to force it to white balance. And here's my image before masking. It's all only. And then here's my masked image. So my masked image has all of the noise cleaned up. Then I hit escape to end the image capture, and then this plot comes up. So here I have one dot for each of my objects, and if you look at the red, green, and blue values, you can see that these objects really do represent some objects that are blue, 3 blue objects over here in the corner, one object that is a green object because it has a high green value, and one object that is red because it has a high red value. Now, I would like to be able to capture data points for 2 classes. So up here at the top, before the while loop, I'm going to create a new index called j, set it equal to 1, and then while j is less than or equal to 2, this is the number of classes that I'm going to capture data points for. Now, I'm going to highlight all of this stuff that we did, and I want all of this stuff to go inside the j loop. So I highlight all this stuff, and then I hit tab to make sure it goes into the j loop. Then, inside the j loop, I'll do if j is equal to 1, that is, if it's the first time through the loop, then I want to create a scatter plot, and the color of the points in this scatter plot will be blue, and I'll turn on the hold because I'm going to capture points in another class, and then I want to plot them. So if j is equal to 2, I want to make another scatter plot, but this time the color is going to be red, so that we'll plot all of the data points in class 1 in the color blue, and we'll plot all of the data points in the second class in the red color. Now I can't forget to increment j, otherwise we'll get stuck in a loop. So j equals j plus 1, and now let's try it. Oh, once again, I forgot to put a colon here. I always forget to put colons on my loops. Okay, I'm going to stick my hand in the screen to force it to white balance. And then I'm going to place all of the objects for one class in the image. For this first test, I'm going to separate the objects by color. So I'll start by placing all objects of one color in the screen. I'll do red, and then when you hit escape, it will capture the data for the first class. Let's take a look at these other images. Here's my all only. I see the 3 objects, but I have a lot of noise. Then here's my masked image and the noise has been cleaned up, so everything looks good. I'll hit escape to go ahead and capture this data. Then it loops through again because now we're going to capture the data for the second class. So I'll remove my red objects and now I'm going to stick some blue objects in the screen. The blue objects will be for class 2. I want to arrange my objects so they're in view and none of them touch each other or overlap. And then I'll check my other images. Here's my all only image. And then here's my masked image. So everything looks good, but I have some noise. This noise is going to cause some problems in my data capture. I'm going to continue to run it here and show you the effect of this noise. And then I'll show you how we can fix the noise. When I'm ready to go, I hit escape and then we'll look at this data plot. You see how my red points are split in two. One of these groups are my actual blue data points representing the blue objects, and the other group is the noise. However, notice that my blue points and my red points are completely separable. That means that the features I've chosen, red, green, and blue, are sufficient for separating out the data given the way that I have classified them. Now, if we go back to the code, let's try and fix this noise. I'm going to fix the noise by changing the sensitivity here. So my blue is being thresholded 50 and my green is being thresholded 20. So I'm going to reduce the sensitivity of green. And then I'll run this again. And I'm hoping that reducing the sensitivity to green will reduce my noise. So I have a pink background, so I stick my hand in the view to try and get it to white balance. There we go. This time I'm going to sort the objects differently. First, I'll do all circles. My all only image picks up all of the circles. And my masked image picks up all of the circles. So I'll hit escape, capture the data. Now for the second class, instead of putting circles in, I'm going to do squares. So in the first example, I sorted the pieces by color. In this example, I'm sorting the pieces by shape. And we're going to look at our data and see if the features that we have are still good features. So I'm going to try to arrange these squares so that they're all in view and they're not touching each other or overlapping. Then I'll check the all only. It looks good. It picks up the three objects and it has lots of noise, but that's okay. It's the all only image. The masked image also has all of the objects and it has very little or no noise. So that's great. I'll hit escape and we'll look at this data. So in this plot, you can see that the red points and the blue points are not separable. That's because red, blue, and green are not good features for telling the difference between circles and squares. So this is an indication that we need to try to find some different features to use to separate our classes. We already have the size feature that we've calculated. Let's try and use it. So to find the average size, I have to take the size that we're already calculating and I need to divide it by 255 because the pixel value is between 0 and 255. Now let's replace the green feature with the size feature. So I'm going to plot average size for both of the classes. We need to remember that size is taking the place of green. So when we see our plot, the green axis is now size, not the green value. So I run the code, and the first thing I'm going to do for my classes is put in the circles. I'll remove these squares from last time. I'll put some circles back in. Try to get them all on the screen and not touching each other. And before I hit escape to capture the data, I'm going to check my all only image to make sure that all of the objects were actually captured. It looks good, 3 circles. Then I'm going to check the masked image, and I want to make sure that there isn't any noise here. Then I hit escape. Okay, I remove the circles now, and I want to put on the objects for class 2. So I'll put the squares back on. Let me get these squares all in view and not overlapping. Then I'll check the all only image. Looks good, I can see all 3 squares. Then I look at the masked image to make sure there isn't noise showing up. Then I hit escape to capture the data. So remember that the green value here is now actually size. This data now is separable. This is telling us that the use of the size feature is good for the kind of classes that we have decided to sort the data into. The blue value and the red value really aren't very useful here for separating the data. So we could actually use just the size feature and no other features in order to separate the data if this is how we were going to classify the data. So here's what I want you to do. See if you can come up with one other feature that you can extract from the images of the objects and write some code to extract that feature and then plot the data with your feature. Some possibilities that you might want to think about include the height of the object or the width of the object, or maybe you want to use both of those in order to get the aspect ratio of the object, or you can come up with any other feature that you want.